Hello and welcome everyone to the October meeting of Integration Down Under. So we've got a really good topic today. I've been doing a lot of stuff around the functions and especially some of the durable function stuff I've been looking at lately. So it's going to be a really good topic tonight. So let's go on. So our organizers for Integration Down Under are Martin, Dan, Renee, and Wagner. I think Wagner at the moment's in Vienna at a conference, and Martin's on his way home from work in Perth because it's with the daylight savings change, it's like 4 o'clock in the afternoon for him. So let's see. And then our presenter tonight is Paco, the Azure Durable Functions 2, basically going into a bit of that. Paco is another Azure MVP, and I used to work with Paco when I was at Mexia. Paco's now at Deloitte, who purchased Mexia a while ago, about this time last year or a little bit later. So let me go ahead and hand over to Paco.
Thank you so much, Bill, again, and thank you everyone for joining tonight. So the topic of tonight is Durable Functions 2.0, which is currently in preview. It's gonna be released later this year. And this framework allows you to build stateful serverless functions on the cloud. So again, my name is Paco de la Cruz. I work for Deloitte Platform Engineering. I'm a Microsoft MVP. You can follow me on Twitter. You can also follow my blog posts on my blog, pacodelacruz.io. The sample code that I'm showing tonight is on my GitHub, and the slides will be available on my SlideShare space. So the agenda for tonight, first we're going to have a brief recap of what serverless and Azure Functions are, then what's coming on Durable Functions 2.0. Then we're going to discuss the different patterns we can implement on Durable Functions, then different types of functions we can implement with this framework. And then we will go deeper into durable entities, what the value of this new feature is, and then a demo. So I'm going to show you how I built a serverless stateful request bin that you can deploy and own yourself. So you can inspect your HTTP requests or your webhooks or even your event grid events, and then Q&A at the end. Before we start about talking about serverless, so let's talk about the spectrum of cloud computing. So there are different offerings on the cloud that we can leverage to use to implement our solutions. And some of them offer us more control, and some of them would give us more productivity. So in the beginning, everything was IaaS, mostly virtual machines, and then we started getting the platform as a service, and then the next wave of evolution was serverless functions as a service. We also have containers as a service. We also have managed Kubernetes. And we also have low-code platforms, which on Azure would be these offerings. So we have VMs, we have app services, Azure Functions, LogicCaps, container instances, and AKS. So tonight we're going to focus on functions as a service, which is Azure Functions. So let's talk about the benefits of serverless functions as a service. Well, first is you have server abstractions, and this gives you a lot of productivity for the operators. So you don't need to patch VMs, you don't need to worry about any of the underlying infrastructure. It's all managed for you. That also includes all the scaling, all the load balancing, and all the high availability. So it doesn't matter how many instances of your functions you're running or your application you're running, there is a load balancer over there. And then if a VM dies, the cloud provider will, there's a bit of noise background. Yep, a bit better now. So all is managed for you. And you might be thinking, well, I'm already getting this with my platform as a service offerings like app services. So what's the difference with serverless? So there are some differences. The first one is scaling is based on events. So if you compare functions with an app service or a web app, for example, a web app scales based on CPU or memory. In functions, you scale based on events. You also get some programming models, and this gives you a lot of productivity. So you focus only on the code that provides business value, and all the plumbing to connect to queues or to blob storage or to Cosmos DB or to receive HTTP is already implemented for you. You just need to implement the bindings on or the programming models. And also you only pay for what you use. So if your function is idle, you need to pay for that time. So functions in a nutshell. So we have event triggers. Our functions can be started when there is a new event, create event, or when there is a new file on the blob container, when we have a message on service bus, when we have a new document on Cosmos DB, and so on and so forth. So these are event triggers, and then this will trigger my code that is in my Azure function. I can write my code in C#, F#, Node.js, Java, Python, or PowerShell. And then this will produce some outputs. And again, I can send a message to a queue or send a notification, send an SMS via Twilio, or send an email via SendGrid, post a message on Cosmos DB. So yeah, so this is pretty much how functions work. Now that we understand how functions work, so what's Durable Functions? So Durable Functions is an extension on top of Azure Functions. It's based on the Durable Task Framework, and the first implementation uses Azure Storage, but now they are allowing you to extend or to provide your own to implement your own provider for persistence. But this persistence is managed and abstracted. You don't need to worry about all of this. And Durable Functions allows you to implement not only stateful workflows, but now they also allow you to implement stateful entities. And at the moment, you can do this with C#, F#, and JavaScript. So Durable Functions 2.0 is coming later this year. At the moment, we have the beta 3 preview release. The main feature that is coming in this release is durable entities that we're going to cover tonight. And this is very similar to the actor-like pattern or actor pattern like aka.net or Orleans. They will also provide the ability to have HTTP calls from your workflows, from your orchestration function, and you will be able to use managed identity. So for example, if you're accessing a resource that is protected using Active Directory, you would be able to use the identity assigned to your function to make that HTTP call. As I mentioned, now you will be able to bring your own state provider. So for example, if you can, instead of using Azure Storage, to use Redis for hosting your durable functions on-prem, you will be able to do that. They are providing also some improvements for testability, so you will be able to better test your durable functions. And they are also providing a Roslyn analyzer. So whenever you have some code that is not compliant with the requirements of an orchestrator that makes your workflow non-deterministic, you will see these warnings in your editor like VS Code or Visual Studio. Okay, so now let's talk about the different patterns we can implement on durable functions. So the first one is function chaining. That means we can have different nano-services, and these nano-services can be executed sequentially. So let's say you have function 1, 2, and 3, and then function 2 is executed once function 1 finishes, and it uses the output of function 1, and so on. So function 3 again executes when function 2 finishes using the output of function 2. So we can implement this using queues or using HTTP calls. But what happens, for example, if function 3 fails? So how do you implement error handling, or how do you monitor the behavior of your decoupled functions. So the advantage of durable functions in the workflows is that you can see this in code, and you can implement this in code. You can implement your exception handling and retries and all that. You can also implement fan out and fan in, the fan out and fan in pattern. So let's say you need to implement different tasks in parallel. You can implement that with durable functions, and then when all the parallel threads have finished, then you can continue with your orchestration. You can also continue when the first of these tasks finishes. So you can continue when all or when any of the tasks finishes. You can also implement asynchronous HTTP API. So let's say you have a very long-running API that you don't want the clients to be waiting until the long-running process finishes. You can durable functions allows you to have a status endpoint. So you trigger your function, and then the client can be polling that status endpoint to be polling until your function finishes. And your function will be able to provide a status or a progress of the processing back to the client. We can also implement a monitoring pattern. So let's say you have an API or a resource that you want to monitor with an endless loop. So you can have an orchestration that checks the status of your API, external API, every 5 minutes, for example. And then if there are some conditions, you need to do some logging or raise some alerts. So you can implement this with durable functions. You can also implement human interactions. So let's say you have a approval workflow that has to be that you have some human steps or human interaction steps. You can implement this with durable functions. Or, for example, let's say you trigger a build and then you're waiting for a webhook to continue your processing. You can also wait for those external events. All these patterns were available on Durable Functions 1.0. With 2.0, they're releasing a new pattern, which is durable entities. So with durable entities, what you can do is using the programming model, you can have these stateful entities that, and then other functions can signal your durable entities, like, for example, to mutate the state of your entity. Orchestrations can query the state of your durable entity, and any other function can get the state of your durable entity, and orchestrators can call your durable entity. So if you need something to be request response, you need to do it through an orchestrator function. But the idea is that you can have any type of entity. I mean, entity is really a very broad word, but you can have any kind of information or yeah. So imagine like if you were implementing this with the repository pattern or through a database, so you can have any type of entities here, and all the persistence layer or persistence logic is abstracted from us. Quite powerful. We will see this in the demo. Okay, so there are different types of functions that we can implement in durable functions. So we have the client, we have the orchestrator and the activity. The client and the activity functions are stateless, and the orchestrator function is stateful. So the client can start an orchestrator, can query an orchestrator, can terminate, and can signal an orchestrator. The orchestrator is the function that implements the workflow. We will see some code in the following slides where we can implement the exception handling, we can implement the retries, and we can call the activities. We can also call another orchestrator functions that we can call sub-orchestrations. And we can also set the status of the orchestrator in the case a client needs to get custom status for the orchestrator. For example, for that asynchronous HTTP API that the client had to request for the status, we can set that status here. And we also have the activity functions that are meant to perform a single step and are meant to do all the I/O. So the orchestrators shouldn't do any I/O. Now we can make HTTP requests, but all other type of I/O should be done on activity functions. Now on Durable Functions 2.0, they introduced a new type of functions, which is the entity functions. As I mentioned, this is another stateful function, and the state here is related not to the process, not to the workflow, but to an entity. So we define the entity that we want to persist the state. Okay, so as I mentioned, durable entities implement an actor-like pattern. So it's very similar to the actor pattern, but has some differences. So similar to the actor in, let's say, aka.net or Lins, these entities are reachable via an entity ID, and we define this ID. Operations are executed serially, so we make sure that there are no race conditions. So every time we send a signal to the entity, these signals will be queued in a queue, and then the framework will execute these messages in order. These entities are created when they are first called or signaled. So we don't need to create an entity. We just either get the status or send the status, and these entities will be created. When these entities are not being signaled or called, they are unloaded from memory, so we don't need to be paying for that time. So when the entities are idle, are persisted into storage, and we're not paying for that time, that execution time. Now, there are some differences with other actor models. The main one is that because we have orchestrators, now orchestrators gives us some additional controls. For example, we can have some distributed locking. So we can say, let's say we are transferring funds from entity A to entity B. So we need to first credit entity A and then debit entity B. So we can have these special sections or protected sections in the orchestration function to have this distributed locking between multiple entities. Orchestrations also allow two-way requests, so not only signaling, but also expecting a response from the entity. Other entities and clients can only be one-way, can only send one-way messages to entities. In this case, it's like a signal. And this framework is focused on durability, not on latency, because we have well, by default, we get storage account persisting all the state, and well, storage has some throttling, and everything is implemented via queues, by messages in a queue. So there might be some latency in this implementation. So we need to be aware of this, and we need to understand that this framework is more focused on durability rather than latency. Okay, so this is just to show you how an orchestration function looks like, and this is a very basic one. So in this case, as we can see here, we're calling three functions: F1, F2, and F3, and then we call them sequentially, and then we also have an exception handling block here that we can do some compensation on or some kind of implement some logging or something like that to mutate the state that we're interacting with in any of these functions. As you can see, all this is very simple. So 3 lines of code, then we are doing some function sequencing here, and all the magic of sending messages by a queue and then waiting until the function finishes and then continue with the next function. All that is happening within the orchestrator, and it's all abstracted from us. So it's very, very easy to implement. as I mentioned, we can implement just the normal constructs we are used to in C# to implement exception handling. And we can also implement retries when we're calling these activity functions. If we wanted to implement the fan out and fan in pattern, again, very few lines of code. So for example, here we are implementing a loop, and we are getting from an array, from a list of tasks, from an array of objects, we are creating a new list of tasks, and then we call the activity functions, and these are all being called in parallel. And then when all the functions have finished, we can continue with our processing in the orchestration. Very few lines of code, and we can do all this. And the client, again, is very simple, very few lines of code. So we have an orchestration client, our durable client, and this client gets the data from the bindings, and then we can call a new orchestrator with this input data, and then we just need to check the status. We get the instance ID, and that's it. Very simple. So these patterns were available in Durable Functions 1.0. So now let's talk about durable entities. So the durable entities are, again, very simple. So we can think of this as something like the repository pattern. So here we have some methods to mutate the state of our repository. So we have a method to add an amount, to get an amount, and to reset the value. And we just need to define this entry point here. So this is where we define the bindings and we are declaring that this is an entity function. Otherwise, everything else is what we're used to in C#. So we have some public properties that are available to any of the other functions, and then these are the mutators for our state of our entity. So again, this is the entry point. Then we have the properties that define our state, and then the methods to mutate the state. Okay, so if you have worked with LogicCaps, where LogicCaps also allow you to implement stateful workflows. So you might be wondering what the differences are between LogicCaps and functions and durable functions. So first is LogicCaps only gives you stateful workflows, so the stateful process, but doesn't give you stateful entities. So now with Durable Functions 2.0, now we have these durable entities. LogicCaps, you use a visual designer, and then behind the scenes there is a workflow definition language, which is in JSON. In Durable Functions, it's all code. So you use the code you like C#, F# or JavaScript, and you use the construct that you are used to. So depending on your preference, you would use one or the other. One of the main differences is the amount of connectors available on each of the platforms. So LogicCaps gives you 250 plus connectors, and Durable Functions has roughly 20 bindings supported. So this is inputs and output bindings. So if you need to integrate with many different systems, probably LogicCaps would give you a lot of value. But if you just need basic protocols, Durable Functions might give you all what you need. Durable Functions have a portable runtime, while LogicCaps, they only run on the cloud. The monitoring of Durable Functions is not as extensive, so it's all based on app insights and APIs. You can call the management API, whereas LogicCaps gives you very rich monitoring and management tools, and especially for the ops, this is a good capability of the platform. Durable Functions can be deployed serverless, where you only pay for what you use, but you can also deploy them in a dedicated premium instance or even in an isolated environment using the app service environment if you want to be fully locked down in your own VNet. And LogicCaps, you can deploy them again in the serverless mode, where you only pay for what you use, and you can only implement them in a dedicated environment locked down in your VNet using the integration service environment. You can read more details of this comparison in my blog post listed here. Okay, do you have any questions so far before we move into the demo?
There's no questions at the moment, so.
Okay, cool. Okay, so let's go move into the demo. So as I mentioned, I'm going to show how I built a stateful serverless request bin. Let's discuss why having your own serverless request bin is a good idea. So if you have used any of the public request bins, so the original one was quite nice, very lightweight, and then it was shut down because of constant abuse, so they had to shut down. But now you have so many options available again. And all of them are free, and you can send your HTTP requests and inspect them. The main problem with that is that sometimes you need to send payloads with sensitive data. Sometimes your body is sensitive. Sometimes your JWT headers are also sensitive, or you're using basic credentials and all that. So you don't want to send that to a public repository, and you don't know what they do, right? You don't know if they're logging your requests, or you don't know if someone else has got access to your request bin ID. So then someone else can inspect all your requests, right? They can get access to your JWTs, or they can get access to your sensitive payloads and all that. So you could potentially deploy your own request bin in your own container, and then you would only have access to that container. The main problem with that is that if you do it using Azure container instances, then you would need to be paying for that request bin even if you're not using it. So if you want to have a request bin that you only pay for what you use, and even more important, that you get all these free executions per month on the cloud. So I think it's a very good idea to have your own serverless request bin. You can deploy it to Azure, and let's see how we deploy it to Azure. Let's understand the solution and let's test it. Okay. So this is the repo where the serverless request bin is. So all the source code is there, and you can deploy it to Azure here. So if you click this button, so let's just deploy a new instance. So we're gonna use this resource group. So let's go to this resource group. This resource group, I'm going to create a new set of resources. I'm going to call them down under request bin. So I'm going to create this new set of resources. I'm going to say deploy app insights on this region. I'm using liquid templates to render the content. We can see that in the code. I'm using this template. I want to store 20 requests in my bin, but you can tweak this in your deployment. I want to only store the first 128,000 characters of my body. You can, again, if you're deploying this on your own, you can change this value, and then function apps and app services add some headers to the request. So you can say, please ignore these headers so my bin is a bit cleaner. So all these settings you can change, but you can keep them by default as well. So the only thing you need to specify is your resource group and your app name. So let's deploy this. So this will tell me which resources are going to be deployed. So it's going to be a storage account, and a function app, and application insights for monitoring. So let's deploy this. So again, we don't have anything here called down under. So let's deploy it. And while this is going to take a couple of minutes because it's going to create all the resources, and then on top of that, it's going to deploy the code coming from GitHub into functions. So let's explore the code. So this is the code again. This is all open source. You can have a look at this. So we have a function, HTTP triggered function that persists the request into the bin, and we're using durable entities here. So what it does is it's a HTTP triggered function. We're using the durable client, and we're receiving a HTTP request, right? And we receive the bin ID as part of the route. So some logging, I check the bin ID if it's valid. I have some rules in my service layer, and then I get the description. So I get a HTTP request. I translate that into a model that I have here. And then I encode the bin ID, just in the case there are some special characters so I can use it as an entity ID in my entity functions. And then what I do is, this is where the important bit is I have a client, the durable client. I'm saying signal this entity of this interface. This is my ID, which is encoded, and we're going to call the add. So add to my bin with this ID, this request description, which is just the instance of the model. And then some logging, and then we return HTTP 200 OK. As you can see, this is very, very simple. And we're calling the durable entities. So now let's go to the durable entities. We only have one, and we have the interface. So the code of the durable entity is actually very, very simple. So we have an entry point. We have here, we're saying this is a function, this is the name, and this is again just an entry point. We're telling, so we're using the bindings. We're saying this is an entity trigger. We have a context, and that's it. Very, very simple. We just need to return the context. And we define how we're going to persist the state. In this case, it's just a list of this model. So I can show you what I have in my model. Just I'm storing the method of my request, the path of my request, the source IP, the timestamp, key value pair for my headers, and a key value pair for the query params, and then just the body as a string. Very simple. So my state is just a list of HTTP requests. The ID is implicit. As we saw when we signal the entity, we send the bin ID, and this is implicit. So we don't need to make it explicit in the entity. I have a constructor here. I'm using the options pattern just to simplify how we're getting the config settings, but you don't need this. So you can even, if you're not using the options pattern, you don't even need the constructor. No need to do any dependency injection in your implementation, probably even simpler. And then the add method, I receive a description. Then to my list, right, I just add a new item. And then what I'm doing here is, if I'm already over the limit of the size limit that I set up in my settings, let's say if it's 20, then remove the first item. So I always keep the latest 20 requests. So this is one method to mutate my state add, and I also have another method to clear my bin empty. So I just set my state to a new list, a new empty list. Very, very simple. So this would be something similar to repository pattern, however, it's we could argue that it's even simpler because we only need to implement the methods for mutate the state, but we can even expose the state as public properties, and that's it. We don't even create methods to get any state. So I showed you already how to persist the request into the bin. Let's see how to get the bin. Again, the code is very, very simple. So we have an HTTP triggered function. We are using the durable client. We receive the bin ID, and that's it. Some logging. I check the bin using my service layer. Then I create my bin URL. This is just to show it to the user. Then I encode the bin ID. I get the durable entity ID, which is just @ symbol the name of the entity and then @ symbol the ID of the entity. And then I read the state. So this is where I'm reading the state of my durable entity. I have a client. I have the client that I have in my bindings. I read the entity state. I pass the entity type, and then I pass the ID, and I get entity state response. And this response has two values. So one is if the entity is available, and the other one is the state. So here, what I'm doing, I have a renderer. So this is where all the logic to translate my list of HTTP requests into HTML to be rendered to the user happens. So I'm using .liquid here. I pass the bin ID, the bin URL. I pass the entity state, and then I'm checking here if it's null, and then I pass the request history items. Some logging, and then I return HTML content result. Very straightforward. I can also show you the empty bin function. Again, it's HTTP triggered. The only thing that has to do is just call the empty method here. Very basic. That's pretty much it. So let's see if the deployment has finished. Yeah, the deployment has finished. So if we refresh the resource group here, now we should have down under request bin set of resources here. So we should be able to call this new function now. So I'm using VS Code REST client extension. So this allows me to send HTTP requests from VS Code. But I'm telling VS Code here, the extension is, okay, this is my base path, and this is my bin ID. Send a request to my base path bin ID, and then use these query params. So let's see if we can call. So down under request bin functions, let's see if everything goes well. I made something, I don't know if it's smart or stupid or brave. Oops. Click refresh instead of intro. So down under durable request bin. So I found a bug in my last, all good. In my last rehearsal, my last reel, and I decided to fix it just before the presentation, but everything is working okay. So this is the request bin that I just deployed to new function app, and it's telling me request bin ID is empty, send your request to this URL, right? So now I have my own private request bin. My code doesn't have any authentication, but you can even enable authorization methods in your function. So you can implement any of the easy auth, or you can implement also authorization at the function level. So then only with the function key or function code, you will be able to get the request bin history. So let's send some requests to this bean. So I'm going to send a get request. Again, this is my base path and this is my bean ID. I'm going to send, let's add a new query param here. Let's say session equals integration down under. So I'm going to send a new get request to my request bean. So this is my bean ID 1, 2, 3, 4, 5. I just sent it, received it. So if I refresh this, now I have a get request in my bean, right? So I have, as we can see here, I'm getting the bean ID. So this is, sorry, the bean URL. I'm getting the path, the method, the timestamp in UTC, the source IP, the query params. So the new query param I just added, all the headers. So in my request, I had one single header, but right? And then because this is overridden by the host, this was just one of my tests, but yeah, so I can see all the headers and many of them are by default, like the user agent and all those. Let's create a new request here. So I'm gonna add a new custom header here. I'm gonna remove this. So I already have my custom header here. Second header. Okay, so a new request. This is a very sensitive payload, by the way. That's why I'm using my own request bean. I'm sending a post request. So let's refresh my bean. Now I have post request. And I have the header that I'm sending, right? So as you can see, I'm able to inspect my HTTP requests. And this is my own stateful environment, right? So I can add security to this, the get bean function, and then only myself will be able to see my requests. Cool. So I can send more requests, have patch, head operation, options operation. Now I have all the requests here, right? So the request bean is, the serverless and stateful HTTP request bean is working as expected. So as I mentioned, I'm using request.liquid rendering here. So just to show you here, so this is my rendering service. I use a liquid template that is here. I'm just creating, by liquid, I'm creating just a HTML response that I'm rendering from the backend. So probably not the most elegant solution, but the simplest, because I don't need to have a single page application that has to be hosted somewhere else and then use a CDN to put everything together. So this is just probably the simplest. What else? I think that's it. That's all the important bits. So in my local settings, I have the storage account, I have the renderer. In this case, I only have the liquid, only the liquid implemented, but I could change that. I have the template. So these are all the settings that I defined when I deployed it to the cloud. Cool. Okay, so the request bean is here, so you can access the source code, but you can also deploy it to your own Azure subscription, as you saw. Very, very simple. Well, that's pretty much it. So these are durable entities and these are durable functions 2.0. And as you saw, the demo was very simple to implement. I would say the hardest part was really the liquid template and the rendering into HTML. Otherwise, the implementation of all the plumbing and all the implementation of the durable entities and all that was quite straightforward, very few lines of code as you could see. So I don't know if you have any questions.
There's no questions. Dan made a comment. Nice job, Paco.
Thank you.
Yeah, so if anybody has any questions, just type them into the question window or just unmute yourself if you want to say something.
Yep. So okay, there's some additional resources, so you can follow the functions team to be aware of the latest releases and latest updates. You can also see the documentation of Durable Functions and Durable Functions 2.0. They also have a live webcast that they have probably every month. You can also have a look at the repos, so the runtime and all the engine behind Durable Functions is open source. The extension and the implementation for C# and Node is available, so you can even contribute or see what's happening behind the scenes, and there are some samples as well. As I mentioned, so the source code is available on my GitHub. I will be uploading my slides to my SlideShare space, and I will be also publishing a blog in the following days explaining the serverless request being using Durable Functions. And that's pretty much it. Thank you so much. Back to you, Bill.
Yep, and the recording will be up in a couple of days on the Integration Down Under in our web, our YouTube channel. So you should be seeing my thanks for attending screen. And that's pretty much without any more questions or anything. I don't see anything in the question windows or anything. So thanks everyone for attending. Thanks Paco for presenting, and we will see you next month. Thank you very much.
Thank you so much. Talk to you later.